Welcome to the Minnesota Astronomical Society's February 2023 meeting. It is going to be special tonight with our budget happening, which we will eventually get to. The opening screen that we have here is the comet picture from Mr. Mark Jobe. I think it's pretty good. If anybody else has ones that they want to send in and share, definitely do that, either to info secretary or on Slack. We'll get it posted. But we also want to see it. So I would like to introduce the board. Sorry, brain's a little funky tonight. I am Trina Johnson, the president. John Zimmich, I believe, is online, coming from far away. Dave Faulkner is in the house. He's our secretary. Matt is our treasurer and local technology guru, making us visible and voiceovers. Conrad, I do not see in the room, but Ahmed is here and he is helping take care of our ballots that are in-house for everybody. So welcome and thank you. We would like to welcome the new members. I believe we have 14 up there. But we are at 678 total members, 173 patrons. So thank you very much for everybody who's a patron. Appreciate that. 475 regular and 3 honorary and 30 students. So welcome all you young people. We hope that you love our little obsession. And I would like to thank all of our volunteers. Especially the executive board who is working through all of the budgets that you will be able to see coming up. All of the members of ELO who helped out at Baylor Regional Park with the Candlelight Ski and Hayride this last weekend. All of the committees who were able to actually get all of your budgets done and in. We appreciate that. Steve Emmer for the last BSIG and for helping out with the membership tonight for verifying registered users. And then there's a little picture on there, and I believe that is Gus from the Tucson, Arizona Astronomical Association. Hopefully I was close. Anyway, that was arranged for our LX200 to be sent down there and donated to them. They are super excited for that. And that was a joint effort between Mark, Merle, John, and the other John that is part of the Tucson Club. John Mead. Lots of Johns. And they are thrilled, and they can't thank us enough for sending that down to them. They're super excited. Our next meeting will be in a month, March 2nd instead of February 2nd. That's kind of cool. 3222. Oh God, I put 22. I am so sorry. I'll have to correct that. That was a year ago. Same time, same place. And hopefully a little bit more fun, but a little less numbers. Just as a reminder, we have Slack. The board uses it. I use it at work. We'll get to there. This is there. The MAS is on YouTube. This meeting will be posted on YouTube once we get done with tonight, and it'll be up there in a couple of days. We have our monthly meetings. We have the special interest groups like this weekend when Dave Faulkner does his presentation. Is it this weekend? Yeah. Oh, yeah. Yeah, this weekend. Sorry, that's on our next one. So that one will be up there as well. So, yeah, yes, for the B6. So check it out. Check it out. Loanerscope program. Oh, such fond memories. I used to be the Loanerscope coordinator too when I first joined the MAS. It allowed me to kind of trial run every single telescope that was out there. It was really great. I believe we have 15 or more Loanerscopes, which everyone can borrow for a month. You get the telescope, the bag, eyepieces, some instruction. You pick it up at Antone's house, bring it back a month later. And it doesn't have to necessarily be in your backyard. You can take it with you to the lake house if you want for the month, although it's kind of cold, but go right ahead. But the form that you fill out is online, just at mnastro.org. memberships. And then you get the whole list up there. We also have the master, I forget what it's called. The DVDs, master courses, the great master courses. Those are DVD sets. I think he's got about a dozen of them that have been donated to us. Wonderful information. And, you can have it on the background and you can still listen and learn as you're going. I have one right now. It's talking about the solar system. Not that I don't know it, but it's a way to know it a little bit better. And considering Jupiter and Venus and Saturn are really bright right now. This is great. COVID, everybody knows COVID as we were talking about it. Stay home if you're sick because we don't want to hear you coughing. Thank you very much. Events for the next meeting. We have February 4th. There's a family fun night at Bellwin from 5 to 7. Granted, it might be a little bit cloudy, but it's a good way to come out and just hang out with the people that are Bellwin members and showing off the telescope that's out there in the observatory. I'm going to be out there. I know Dave Johnson's going to be out there. We could always use a couple more people, just keeping things in line. If you wanted to bring a telescope, you could set it outside or even binoculars. Set those up as well. We've got our full moon that is fighting the comet's brightness. So, but it still can be seen. I've seen the comet. I took my binoculars out. It was 0 degrees, but I did it for about 30 seconds. Sure. How many people in house have seen the comet? Whether 1, 2, 3, 4, 5, 6, 7, 8. Not bad. Did you use binoculars or did you use a telescope? Well, you used a camera. You took your binoculars. Excellent. See, it's a good binocular object. We've got a couple of close stars to the moon. Dave Faulkner's BSIG on Saturday at 1 o'clock. 11. Oh, Saturday 11th. Okay. That's not this weekend, is it? No. Sorry, in a week and a half. I was thinking it was this weekend. I'm sorry. I was excited. I wanted to hear it. Yes. Okay, a week and a half. There we go. And then at the end and March 2nd, we're back here. Little public service announcement, Planets in the Park. Michael Copper is hosting that on February 25th at Pershing Field Park. He would love to have some people come out and help him with that. It's going to be from 7 to 8:30. And if it's cloudy or inclement weather, I believe him and his co-host is scheduling some indoor activities and indoor speakers. So give him a shout if you can help with that. I think there's something on the forums. If not, just send an email to info and we'll get you. Here we go for the BSIG. There you go, short version, even though I've already talked about it. February 11th, 1 o'clock, Dave Faulkner. His trip to Chile. No, not Chile. What did I get wrong?
Slight correction there. It is the ASIP ambassador trip. So it's Astronomy in Chile Education Ambassador Program. This was not a NASA program. So
I'm sorry.
Okay, so that's okay. I just wanted to make sure people are clear that we're not talking about NASA stuff at all. So.
Okay, thank you. Thank you. My apologies. They never know you to do other things. So. Gemini articles. I know there's some coming out for Father Brown. I believe that's up on the website already. So go out there, read it. You might have an article that you wrote, and since it's your fellow members that are writing every article for the Gemini, and see what they're up to. I mean, every single one has been very interesting. Because
Gemini article on the creation of the fascinating.
Yep. Yeah, I haven't read it yet, but it's very cool to see the history of ELO in the Gemini. Just a reminder, if you want something in the weekly email, send it to secretary by tonight in order to be published on next Tuesday. Thank you very much. Astronomy League Awards. I know Jerry is doing fun things, so he hasn't been doing this for a little bit, so I get the pleasure of doing that. And we have one this month. We have Mark Peterson, got his Lunar 1. Congratulations. He is in-house. It's a good program. If anybody is interested in starting it or has questions about it, let me know or let Mark know. We can answer some questions and offer some tips and tricks. So, and as Jerry says, which I love this very much, get out there and observe. Lunar 1 is a observation award that is completed for the Astronomical League. And when you go through all of their qualifications, and it's basically watching the moon for a month or longer, it depends on what you take, you have 100 objects that you need to find, and just jot down date and time that you've seen it and can verify that you've seen it. And then you get on the moon, and then you get a pin and a certificate. And I can show you the pin later. It's really cute. It's fun because when you get Lunar 2 completed, it's the first quarter and third quarter moons. So it makes a nice little set. And then we have Better Know a Constellation. Tonight's presentation is going to be by Ben Husset. Hopefully I said that right. On constellation art. And we are looking for a volunteer to do April's. So not next month, because I want to give as much time as Dave needs. So next month, give us a shout. And we'll get you all set up and qualifications.
Madam President?
Sure. And then also next month's meeting is going to be by Dave Faulkner as well.
A long time ago, I started Better Know a Constellation inspired by a similar program run by Stephen Colbert on the Colbert Report, Better Know a District. So, and it's still going, I'm amazed. And very, very pleased. I was, through all the Better Know a Constellation stuff, people would often include a slide of the historical, image of the thing. And I was always sort of fascinated by that image. So thought I'd do a little history about those images. Because, since before history started, people have been looking at the stars and making up legends and stuff about the night sky. Currently, the earliest known one is from 30,000 BC, in which they found a carved tooth that they think was Orion. And on the back, there's these little pock marks, which they thought was equal to the number of days that Betelgeuse is visible from that location. I think it was found in Germany. Yeah. So a little bit later on, this cave painting 21,000 years ago is an oxen or a bull, and it's got these little dots. See, can we put the mouse over? I have to go up. Here we go. Here, and they thought, well, this is obviously Taurus with the Pleiades. Of course, all these things are subject to interpretation. There's some dispute as to, is this really that, or is it, dear nephew Gobo type of interpretation for fans of Fraggle Rock. A little bit newer than that, 18 to 1600, there was this disc, this metal disc found in Germany, which you have a crescent moon, and I just fast forwarded. Come on, there we go. One more. Of a full moon, a crescent moon, and once again the Pleiades. So after that, the Babylonians sort of started the ball rolling with our current constellations. Initially, all of their stuff was done in just a written form, no art per se. but they made up constellations divided into 3 zones: the northern hemisphere, the southern hemisphere, and then where the zodiac hangs out. So, but with that, they have things that you might recognize. We've got a scorpion and scales and a lion and a crab and Gemini and something that is sort of Orion here, and some fish scales. So I mean, all of the stuff that the Greek stuff is, it's all started here. And here you can see sort of where they had mapped these things out to. And of course, you know, Orion with the Pleiades and the bull. So it's been around a while. Of course, the Egyptians copied the stuff, and they have their own pantheon of stuff, but it's pretty much the same stuff. You still have a scorpion and scales and a lion and twins and a hunter with a large stick and a bull. So it's like, yeah, okay, it's still pretty much all the same. Of course, this statue was made in around 150 AD, but they think it was a copy of an earlier Greek statue. And you can see, okay, we have Argo, the ship here. And this, of course, is Atlas holding the globe. And if you look at the other things, you, of course, have the crab and all the stuff that's generally out there. It's all sort of like, yeah, it's pretty much, yeah, once they got onto an idea, it was sort of just passed on and things sort of kept on going. The Chinese, of course, made up their own constellations, which had nothing to do with the Greeks or the Babylonians, but that's cool. But they recorded it around 600 AD, and there's this long scroll that's been copied many times. I think this is like the third generation of a copy, in which they have, you know, over 1,300 stars and 257 different constellations. And you can see an enlargement of one of the panels down here. Around 816, they, you know, before these things were all done on a parchment or stone or something, and they started painting on paper on codexes or, you know, various parchments and stuff like that. So starting to this once again is Orion. But, you know, somebody had to paint the whole thing, and it was very time consuming and very expensive. The Arabs, of course, continued on these things. Of course, all of this was originally inspired by Ptolemy's Almagest. And once again, you see there a version of Orion with the belt stars and the shield and the club, or in this case, looks more like a sword. And then finally, in around 15, someone said, you know, we just got this thing called a printing press. Let's start cranking these things out with a press rather than to have an artist take hours or days to paint one per thing. So, of course, once it was printed in black and white, then you'd have artists come in and sort of do some water color on top of it. And of course, once again, you can see, you know, standard stuff, you know, Ursa Major and Minor and lions and tigers and bears and all sorts of fun. But and of course, there wasn't that much travel yet to the southern hemisphere, so you can see that, gosh, their data for the southern sky is a bit sparse because nobody from northern Europe had gone there and had come back with a tale of what it looked like. Of course, you always have people who say, all those things up in the sky, they're all very pagan. They aren't Christian. So back in 1627, Julius Schuler, who by day was a lawyer and a cartographer, decided that let's rebrand all of this stuff. Let's take out the zodiac and put in the 12 apostles. And Herodotus became the Red Sea, and Noah's Ark, of course, replaced, Argo and stuff like that. I didn't see any real thing, but for most of these things, there's a little links at the bottoms of my notes here. And if you go there, you can look up the Wiki report that gives very high-res detail. Unfortunately, due to time, I can't go into it as deeply as I would like to. But of course, Orion became Saint Joseph, and Cygnus became Saint Helen. We still have sort of the cross shapes, And to his merit, he did have the raw data per se. He did just give you the star map, and you can connect your dots however you darn well felt like. Speaking of connecting the dots, in 1786, Alexander Rule said, just make stick figures. It takes too long to draw all these, actual, almost all looking like something types of people and animals up there. Let's just draw stick figures. So, yeah, very thin-waisted Orion. So, Alexander Jameson in 1822 came up with a very nice book that had 33 maps that had some really decent data. It wasn't, and this is when you start to get, what you classically think of the artistry of constellations and stuff like that. Now 2 years later, in England, Uranus Mirror was published. It had 32 astronomical cards, and the publisher or the author was anonymous, but they came out with some cards that looked a lot like this. This is a replica. But the interesting thing that they had with this was that they had punched little holes. If you held up to light, you could see. Now, of course, in 1824, they didn't have cell phones with lights in them. They had candles, so quite often a lot of these cards caught on fire. If you want to see these, I'll pass these around. Oops, oh dear. It has nothing to do with that, I don't think. So anyway, just as a benchmark, here's what Orion looked like in this image set. So you can see it's very similar to the one that was done by Jameson, but just a little bit different as to how they grouped it. In 1930, IAU said we want to standardize things, and so they had a guy, Henry Norris Russell, said, okay, we're gonna lock it into these 88 constellations. Excuse me a sec. Can I get a glass of water or something? Anyway. Yeah, that'd be good. Very cold outside and very dry in here. So, Russell decided on the names, and then in 28, Delport said, "Okay, we're going to establish boundaries as to where a constellation is," and sort of that's why we wind up with these things that look like Western states. Of right ascension and declination lines. In 52, H.A. Hooray, a bit more. I only punched out the holes for Orion, so. But who is more known for his Curious George stories, decided to, keep it simple and keep it stick drawings and such that, even small kids can relate to the constellations as such. And sort of doing that. Now, of course, people keep reinventing the wheel. Found this in 1997. Someone decided to rebrand the constellations. Bigger. And oh, okay. Didn't fix that. They decided to rebrand the constellations and get rid of the Greeks and Romans to replace it by Alice in Wonderland, in which Alice replaced Virgo, Libra was replaced by the King of Hearts, Cancer the Crab became the other crab in the stories, Leo, of course, replaced the lion, Scorpion, or Scorpio replaced the lobster, Sagittarius became the White Knight, Draco, of course, became the Jabberwock, and Booties became the Carpenter and stuff like that. So, and so for a moderate fee, the site's still there. Go to globemakers.com. They will. They got various sizes, and you can have it be whatever size that they make, and they can do that. So
was a Corona Borealis the cat?
I'd have to dig into the article. They did have a fairly long list as to what constellations were rebranded, but you can see some of the artwork. There's, of course, Tweedledee and Tweedledum became replaced Gemini, and so it's very, very artful. Now, of course, I was in the bookstore just yesterday, and I found this very interesting book that goes over at a very nice level of detail the things I've been talking about today. You just check that out. It's available where books are sold, type of place, online or in a real bricks and mortar store. And of course, we keep recreating the maps. So, quick question or two before we move on to our main speaker.
Your own collection.
These all those links usually if you go into it, somebody is usually sometimes Library of Congress, somebody is given like a 5,000 by 8,000 scan of all these old documents and put them out there as a PDF free to download. So it's, copyrights have long expired on pretty much all of this stuff. And it's great wallpaper.
Hey, Ben, what about some
Yeah.
of the non-European, like some of the African, old Aztec or the Mayan and such?
That is out there
The
too.
Aborigines of Australia have some of their own celestial descriptions.
There are many different constellation groups out there, and I was mostly focused on the European stuff. But yes, the Native Americans and Central Americans and Africans and Australians and China and Japan and in India a little bit. They're sort of a mix. All have come up with totally different stories. And some of them, instead of having a star pattern, you look at a dark nebula, and that is the constellation. So
So in other words, you can make a whole program of some of the various constellations and how they developed over the years, correct?
yeah, well, I figured once we got through all of the 88 IAU constellations, we could delve into those. But that's up to the next presenter, whoever he or she may be, and I look forward to that.
Well, there's a big project, man.
Yeah, can I grab about a minute to tell you, in my other life, I'm chairing MarsCon, which is a local science fiction and fantasy group. The theme this year is When Books Come Alive. It is March 10th through the 12th. Friday through Sunday is at the Hilton Minneapolis St. Paul Airport. The deadline for the rate increase was supposed to be end of last month. I've extended it through tonight. When you're chair, you get, when you're chair, you get to do that. If you say, Ben, I was just there and I couldn't get in, or you're fighting our Square registration program, we encourage you to just keep trying. Square is trying to figure out why it doesn't work. And so far, we don't have a solution. We just encourage keep on trying. So it doesn't seem to be related to browser or OS or anything. It just seems to be random. The artist guest of honor is Darcy Bell Myers, a book illustrator. The author is Wisconsin's PC Hodgel. The media guests are Bradley and Christine Gailey, who play minor characters in some of the new streaming stuff on Disney Plus. And the musical guest is Bonnie Gordon, who is, if you go to YouTube and look on her thing, she sings popularized Spanish songs done to popular tunes. And of course, our featured presenter is somebody who you might all know of, Astrobob from Duluth. So I encourage you to check it out. And it's in like 5 weeks. So,
Well, thank you very much.
Yeah.
Wonderful presentation. So here we go. And Dr. Rutkowski has a bachelor's of science degree in physics, mathematics from Hampton Sydney College. He has a master's of science in, I think it's what MS stands for, and PhD in astrophysics from Arizona State University. His research is focused on the evolution of young stellar populations in high redshift galaxies and their cumulative effect on galactic and cosmic evolution. The majority of this work relies upon observations of galaxies at ultraviolet wavelengths, and this data requires access to a number of space-based observatories operated by the US and other global partners. So now I'm really going to try and stop sharing my screen, and he can take over.
Okay.
Perfect. I'm not touching anything else. I'm leaving it over to you.
Okay. I just threw this up very quickly as an introduction. Here's me. This is me from quite a few years ago now, but this is the Korean constellation stele that was built in or constructed in 1395. Very many different constellations than the ones we're familiar with, none of which I know the name off the top of my head. But do you all see the first slide now?
We do.
Okay. All right, great. So my name is Michael. I'm a professor down at MSU. Thank you all for inviting me. I really don't remember how I got in touch with Ahmed, but I think this was through, I serve as a subject matter expert or a contact within Space Telescope for these sorts of things. And whatever the case is, I'm happy to be here. And it's been a really interesting first hour or so. So tonight I'm going to talk about something which I don't know how many times you've had someone come to talk about UV astrophysics, because it's a very dull field for those of us who live on the Earth. And the reason for that is because we have an atmosphere, thankfully. I'm going to try to walk through sort of what we do in astrophysics, why it matters. And then towards the end of the talk, I've really crammed in a lot of information into this presentation. But I want to spend a little bit of time at the very end sort of talking about what James Webb is telling us about the universe, since we've now had it in operation for a little over gosh, a year now, a year and a month. So we have a lot of new results coming through now that the systems have all been calibrated. And I want to finish up with that. So first of all, everyone knows what the night sky looks like. This is an image from I think it's now the largest International Dark Sky Association site at Big Bend, down on the border with Texas and Mexico. And we've been doing optical science in optical astronomy since as long as we've had, I guess, neck muscles, or we could lie on our backs and look up at the sky, because that light comes down to us, and we're all familiar with the way the sky looks. But if I can be a little facetious, this is what the universe looks like when we look at it from the ground here on Earth in the ultraviolet. And the reason that we don't see anything, the reason that this screen is black is because the UV doesn't penetrate down to the ground. And when I say UV here, I mean what astronomers might call the vacuum UV, wavelengths below about 300 or 330 nanometers. So your eyes can go down to maybe 400. The atmosphere absorbs below 350. Below that, you're not going to get any light coming down to you. So that means you have to go elsewhere to get that data you're after. The reason for this is because we have an atmosphere, as I mentioned. Here's a plot of the transparency on the vertical axis, wavelength on the horizontal. And I don't know if you can, I can't see my mouse, but if you look around that 10 nanometer to 1 micron range, there's the optical window, 100% transmission or transparency at those wavelengths. But once you go shorter into the ultraviolet, ozone tends to absorb all of that light, which is a good thing because then we don't get skin cancer and whatnot. But if you want to do astronomy at those wavelengths, you're screwed. There's no way to see through that atmosphere. And no one to date has proposed to blow off the Earth's atmosphere in order to allow us to do astronomy from the ground. The other reason we like to, we get frustrated with the Earth, and this is a little GIF here. This is an image from Subaru. This is staring at the same point of the sky, very high resolution, or a narrow field of view, watching a star as its light comes down to the Subaru telescope in Hawaii. And what you'll notice, of course, is that the atmosphere causes, as we all know, the stars to twinkle. And so for this, we don't want to lose any light. We want to get all the light into the same pixels, ideally, on our cameras. And so we also are frustrated with the atmosphere for this reason. So we go to space. And if you want to go to space, you go talk to NASA. NASA does all of these large missions for astrophysics. And they have a long history, beginning in 1990 with the so-called great observatories, to go to space and put in this case, Hubble, Chandra, and Spitzer in the optical, the X-ray, and the near and far infrared, or near and medium infrared, to get above this twinkling effect, to get up to above the Earth's atmosphere, where all of this light is being absorbed and prevents us from doing this sort of science on the ground. If I were to make a sort of timeline of the history of astronomy, though, in the ultraviolet, there would be 3 people I would point out. The first is the guy who gave us the telescope, that's Galileo. After a period of about 300 years, Henry Draper figured out that he could put a spectrograph on the back end of a telescope and start to take spectra of deep stars. And then it was another 100 years or so until George Carruthers came around and decided to put an ultraviolet telescope into space. Now, before that, they had tried to put small telescopes on rockets, sounding rockets to the upper atmosphere. But the first time we really achieved, the first time we started ultraviolet astronomy was when we went far above the Earth's atmosphere. And that, of course, occurred in the 1960s and 70s. And here is the first UV telescope in space on the platform here. This gold object that you see is George Carruthers' instrument. I think it was Apollo 16. On the right-hand side, you're seeing the Earth as viewed in the ultraviolet, and you see that nice warm glow. That's all of that upper atmosphere. That's the sunlight glistening off of the upper atmosphere, primarily ozone destruction. So that's the brief history of UV astronomy. We have to go to space, which means that we've only been doing it for about 50 years, in contrast to optical, which we've been doing with telescopes for 420 now or so. Oh, my slide is paused. Okay, so why do we care about the UV astrophysics regime? Why can't we do all the science we want to do in, say, the optical or the near infrared from here on the ground? It would be a heck of a lot cheaper if we could, because it's a heck of a lot cheaper to put a 30-meter telescope on the ground than it is to launch a 2-meter telescope into orbit around the Earth. And the real reason, the driver behind anything in the ultraviolet, the reason you do anything in the ultraviolet is because the UV emission is the signpost for star formation. A young hot star like an O or a B star, its spectrum, if you assume to first order it's a black body, the peak of that spectrum where it emits most of its radiation is in the ultraviolet. This is we've known for a few 200 years now from what we call Wien's law. And so if you want to study young stars, you go to the UV to find those young stars. So here's on the left is an image of our local M31, everyone's favorite Andromeda galaxy. You see these brilliant dust lanes, the bright core. You see even a wispy halo sort of flaring up from the disk itself. And then when you go to the ultraviolet, this is an image taken with a now defunct telescope called Galax in the mid-2000s. You'll notice that all of that haziness sort of goes away. What you're now seeing primarily is just the stars themselves, these young hot stars. And because these hot stars are particularly massive, they don't live for very long. And so you see star formation as it's happening or as it just happened. This is everyone knows the color magnitude diagram, I think, on this call. I'm kind of obscured with the little chat window here. I'm going to try to move it out of the way so I can see the figure. Oh, well, I'll just give up on it. So here's the color magnitude diagram. On the vertical axis, you have luminosity or intrinsic radiation emitted by these stars. And on the vertical axis or horizontal, you have temperature. And you'll notice there's this large swath running across the center, and that's where all of our favorite stars that we know and love live. These are the main sequence stars. These are stars which are happily burning hydrogen into helium in their cores. And they live on this main sequence for a very long time, hence why it appears so prominent. But off of the main sequence, you find a handful of stars in the local neighborhood that have evolved away from it. And these are very massive stars. And the age, the time that a star will spend on the main sequence, is a function of its mass, inversely a function of its mass, whereby very massive stars, O and B type stars, 25, 50 times the mass of the sun, they will live upwards of a millionth the lifetime on the main sequence as will lower mass stars like the sun or less. And what this means is that if you want to study if you look in the ultraviolet and you find these stars, you're going to find them where they're born. Stars will, clusters will start to dissociate over time. The Pleiades is falling apart as we speak. These stars are traveling in space apart from one another, from the birth site in which they were formed. But and they did so, they started that process 100 million years ago. In 100 million years, all of the O stars that could have been formed in a young cluster, though, have already blown up. They've already disappeared. And so if you were to observe those, say 10 million years ago, they would have been located at the places at which they were hatched, so to speak. And the reason we care in particular, or another reason why we might care about massive stars, is that massive stars make a horrible mess of the places in which they're born. They're sort of like those petulant children who are, burping and tossing the food all over the kitchen. When they live violent lives, and when they die even more violently still. So here's a zoom in of everyone's favorite young star forming region. This is going to zoom into the plane of the Milky Way. We're going to zoom in on Orion's Nebula here. I'll turn the sound off. We don't really need the sound. So as we zoom in, you see the plane of the Milky Way. You see now Orion's belt. South of that is Orion's Nebula. And as you zoom in closer and closer, you start to realize that the real structure starts to form in this hot gas that's being irradiated by the very young stars in the central trapezium cluster. And as you zoom farther and farther in, you get this beautiful Orion Nebula a light with star formation. There's only a couple. I think there's one O star and a handful, maybe 10 or so B stars in this cluster. But that one single O star is pouring out radiation and ionizing the gas in the vicinity and causing these beautiful filamentary structures to develop. And that's all very well and good, but that's only the local universe. And we want to study how galaxies come to be, and we want to study the full range over which star formation has formed. And so we need to build space telescopes. We can't just study it from the ground. And so here I've shown you our next door neighbor. This is the LMC, the Large Magellanic Cloud. And I put to scale. I hope that someone can point it out for me, that you can see it there. But if you look right just sort of south in this image in the Tarantula Nebula, do you see that little overlaid small snapshot? I've put on here the Orion Nebula to scale with the nearest massive star forming cluster of 30 Doradus in the LMC and within the broader Tarantula Nebula. And what you'll notice is that, this cluster has many O stars, has many of these very, very massive short-lived stars, and it has totally destroyed its local environment. There are tremendously long, many tens or hundreds of parsecs long structures extending up to kiloparsecs out from above the galaxy itself. And if you want to understand how galaxies evolve, because this is truly a destructive process, you're ionizing gas, you're preventing further stars from being formed. If you want to understand how galaxy formation and evolution is affected by these very young stars embedded deep within the galaxies themselves, you've got to have the ultraviolet. So here is another frame in which to consider the ultraviolet, what ultraviolet is telling us about the evolution of galaxies, which is that here's an image taken of the a very deep field called the Goods North field. This is observed at the Restream far UV, so you're looking at about 150 nanometers here. And what you're seeing here, these little smudges that are scattered throughout, these are galaxies. These are significantly massive galaxies, and you're seeing just the hot young stars within them. And what you'll notice is that none of these galaxies look anything like, Andromeda on the slide a few slides before. So the reason we are interested in studying this image in relation to, say, the LMC and in relation to the nearby Andromeda is because the galaxies here, due to the fact that the speed of light is constant and fixed, we're seeing these galaxies as they appeared roughly, in this case, about 5 billion years ago. And so when you look back over the history of the universe, 5 billion years ago, galaxies look very different than they did today. And what we want to do as astrophysicists is sort of connect those dots and try to understand, why do galaxies transform? Why do they grow and evolve? How are stars affecting that growth and evolution? And it seems to be that young stars play an outsized role, these massive stars, and those massive stars are got at with the ultraviolet. So that's why we do the ultraviolet. And over the past decade, I guess this is should really be 2 decades now since grad school. Well, a decade. It's still fine to call it a decade. I've been looking at young, massive hot stars, and I've been looking at them in 2 distinct ways. And I want to try over the next little bit to try to explain as much of the science as possible, but without going deep into the weeds with the details. So I'm going to talk about how we use these hot stars observed in the ultraviolet as tracers of the merger histories and the formation of massive galaxies, and also their role in ionizing the universe that we observe today over cosmic time. So first, massive galaxy evolution. What do I mean? What is a massive galaxy? A massive galaxy is a galaxy which is much more massive than the Milky Way, maybe 10, 100 times more massive. On the left-hand side, if you've ever looked at the Virgo cluster before, here you're seeing M87. This is the massive elliptical galaxy that sits at the center of this cluster of hundreds of galaxies within a large cluster. And the orangish sort of nondescript, uninteresting, relatively boring morphologies, those galaxies on the left-hand side are all what we would refer to in my line of work as sort of quiescent or quiescent massive galaxies. Traditionally, we might have called them, if we were from Edwin Hubble, we might call them elliptical galaxies, because obviously they have elliptical forms. Hubble also went so far as to suggest that the name early type galaxies. And the reason he called them early type galaxies is because he believed that these shapes, in contrast to the shapes of other galaxies that we know of, indicated something about their evolutionary state, i.e. that these galaxies occurred earlier in the universe and they slowly were evolving into the galaxies that we see that we live in today, for example, the Milky Way galaxy. So on the left-hand side, the image represents a selection of galaxies, which we would generically call early types or quiescent or ellipticals. All of these names mean something independent of one another, but they're all sort of capturing the sense of big, massive, rather uninteresting looking galaxies in terms of star formation or gas, molecular gas, so on and so forth. On the right-hand side, we've got a very famous galaxy. We've got this beautiful merger occurring. This is a quintessential spiral galaxy. This galaxy is actively forming stars, so you might also refer to this galaxy as a star-forming galaxy. And Hubble would have called this more of a late type galaxy or a late type spiral galaxy because it clearly has something going on differently in its morphology, its shape, than does the boring old galaxies on the left, these early type galaxies. Here's the original frame in which he arranged these galaxies. So ellipticals on the left-hand side, spirals on the right-hand side. And this is his sequence of nebular types, because at the time we didn't know, we still referred to all fuzzy objects in the sky as nebula. And what he suggested, the reason he arranged this into the so-called tuning fork, is he believed that these elliptical galaxies slowly over time, over the history of the universe, would sort of devolve into these spiral galaxies like the one we live in today. And when he started to make these measurements by being able to accurately measure the distances to these galaxies using Cepheid variables and such, what he found was that the fraction of these galaxies varied. There weren't the same number of galaxies of each type. And I want to call out in particular that irregular galaxies, galaxies which aren't pictured here, but didn't fit any easy classification, these were only about, I think the number is about 2.5%, but the screen is being blocked, so I'm going to guess that it says 2.5% or something of that order. It's very small. It's a few percent, if anything. The rest of the galaxies we see in the local universe, at least in the Edwin Hubble's universe that he observed, were either spirals or ellipticals. Now, there is an evolution that occurs. Galaxies are not simply born as the galaxies we observe them today. When the first galaxies formed, they have evolved over cosmic time to become the galaxies we observe in the local universe. This is happening as we speak. You may or may not know that in about 4.5 billion years, the Andromeda galaxy is going to come slamming into the Milky Way, and we are going to merge together to form a massive elliptical or an early type galaxy. This process has been happening over the 13.8 billion years of cosmic time. And there are lots of ways to transform galaxies from earlier types, these featureless spheroidal galaxies, into the later type galaxies that we all know and love because they're so beautiful to see. And I've listed a few of them off. I put these names in not because I'll quiz you on them, but we have all sorts of funny names we give these processes by which you kill off a galaxy, or you kill star formation in particular in a galaxy. We can starve them by preventing the accretion of cold gas from which to form future stars. You can shock the gas with feedback from AGN or stellar winds or stellar supernovae. You can have gas stripped from the system as galaxies merge with one another. They may make they may kiss one another as they pass by, and the gravitational field will entrain some of that material and drag it out via gravitational forces and primarily pressure between the gas particles. And the question is, well, which one dominates? How is it a 50-50 chance you'll die by shock heating or mergers, or do mergers dominate, or is star formations killed in such galaxies by AGN? We'd like to know that answer. And the tack that I took in trying to answer this, particularly in my PhD, was to simplify the question down into a long observed relationship, which was that early type galaxies, these bland, featureless, dead looking galaxies, seem to have a characteristic size to them. That is, if you look in the early universe, say Big Bang, and then wait 4 billion years and make a census of all the early type galaxies, what you would find is that they sort of lie along a given relation. So the higher the mass of the galaxy, the larger the galaxy size is. And then as we make these measurements over cosmic time, what we find is that as we advance time forward, as we play the movie forward, and mergers and quenching and stripping and starvation and all these things have been occurring within these galaxies, what we find is that this size relation changes. That for a fixed stellar mass, we get a characteristically larger size of the galaxy. And the question is, well, what's driving this? What fraction of these phenomena that I just listed on the previous slide can we attribute to the size growth? And so I'll outline three of these in cartoons. One is that these galaxies physically grow. They accrete stars from the environment at larger radii that causes these galaxies to grow. Another thing that could be occurring is what we call a progenitor bias, which is that we can't find every type of galaxy at every redshift. We're insensitive to some types of galaxies. And what if we had made a census in the early universe, and then we failed to include the galaxies that were actively forming stars in that census, and then we left them off in our later accounting, but these galaxies end up quenching, for example, and they turn off star formation and they appear very red and dead. This would, if you're counting, if you want to make an apples to apples comparison, but some of your oranges transform into apples over time, then you're going to have a bias in your assumptions about how these galaxies are evolving. And the third one is that, well, maybe galaxies grow. Maybe galaxies accrete young, gas-rich little dwarfs around them. And these galaxies, this galactic mass accretes on. It doesn't really grow the mass of the galaxy too much, but it does grow the sizes because you're accreting these stars that exist onto larger radii. But the observable prediction about this theory in particular is that if these small little dwarfy galaxies surrounding a relatively small high redshift galaxy are accreted on, they should bring in fresh gas from which future generation of stars may be formed. And so we should be able to test this prediction, if this is a prevalent mode of quiescence or death of a massive galaxy, we should be able to look at these galaxies in the local universe, and some of them should show evidence of relatively young stars. So how do you find young stars? Well, you find young stars by looking at the ultraviolet. So that's what we did. And the reason we were motivated to do this in the first place is because we see this already. If you look at the Milky Way, the plane of the Milky Way here is in the center. You'll notice the LMC and the SMC. Those are large, massive, or 10 to the 9 billion, or 10 a billion solar mass galaxies hanging out in the local volume. But you'll also find, if you look deep enough, you'll find tens of very low mass, maybe 10 to the 6, 10 to the 7 dwarf galaxies, we call them, which are caught up in our gravitational field. And eventually they're going to be consumed onto this galaxy. And the idea is, well, if we can find these, if there are dwarfs like this around massive galaxies, some of these dwarfs may be bringing in fresh gas. That fresh gas could find its way into the core. It could collapse and form new stars. And we may periodically be able to detect in the ultraviolet, if we look deep enough, we may be able to find evidence of this merger process occurring in galaxies. And so that's what we set out to do with Hubble. And this was where I spent my entire dissertation, is in this field. I'm not there to show you, but if you took your two thumbs and you put them together and you held them out at arm's length, the size of the ceiling that you would cover with your thumbs is about the size of this image. This is an extremely small region of the sky. And yet in this region, there are about 50,000 galaxies. About 2,000 of these are massive quiescent or early type galaxies. And in this field, in 2008, when Hubble was serviced by the last servicing mission, SM4, they repaired and replaced some of the instrumentations, including installing the Wide Field Camera 3, which had a UV sensitive channel. So we could get access to the rest frame 1,000 angstroms, 100 nanometer light that was coming from many of these galaxies. So we could directly probe whether or not these galaxies that were old and red and boring and otherwise uninteresting, whether or not any of these had evidence of star formation. And to show how powerful this is, I have to show you a spectrum. So here's intensity on the vertical axis as a function of wavelength on the horizontal. And if you look at these two plots, you'll see two curves on each one. One of these, I've arbitrarily cut it off at the rest frame optical light. So you're looking at 5,000 angstrom emission and redder. And the black dots are the observed data points for one of these old early type galaxies in the field. And what you'll notice is that if you didn't have any information about the blue, what you would assume for this galaxy is that there are no young stars. The young stellar population is here indicated with that blue curve, and the red population is a very old stellar population with an age of a few billion years. And if you didn't have any access to the UV, you would assume all of those black points were very well fit with the red curve alone. You don't need that blue curve at all. And yet, with Hubble, we were able to look at the ultraviolet. And when we look at the ultraviolet, those 3 points to the far left of this figure, on the right-hand side now, those 3 points are rest frame ultraviolet data points. And it's clear that the red curve, which dies off, old stars don't produce a lot of UV light. It's only the young stars that shine in the ultraviolet prominently. The red light dies off as you get to UV, or the old cell population dies off, but the young population stays relatively flat. And if you take the combination of these two models and the numbers, the ratio of the masses and ages of these populations is in that figure. If you take an old population, 3 billion year old, and add to that a population that's only 280 million years old, and at a mass fraction that is much, much less than 1% of the total mass in the galaxy, you can very cleanly reproduce the full distribution of observed data for these galaxies. So we did this for a sample of about 100 galaxies, and we did the best we could, but we realized we didn't really have enough data. And so for about 10 years, we applied and applied and applied to Hubble to get more data in these deep fields to do the same sort of study. And now we finally have earned that data. They've awarded a large UV program in 2018, and we're now analyzing that data. And the process is basically the same. We want to find old dead galaxies, old early type galaxies at high redshift. We want to look at these galaxies, confirm, in fact, they're really boring looking. So that's the middle panel here. If you look at the rest frame, sort of optical light, visual band light, that's the F125 here. And you'll see they're pretty smooth, featureless galaxies. There's no spiral arms. There's nothing interesting going on. There's no mergers occurring. And then we model that light, and then we subtract off the light to see if anything remains. And most of the time, the model that we use, which is the model we derive for low redshift or local galaxies that are old like this, fits pretty well. And then we look at the fraction of those galaxies that look old and red and dead and are massive and otherwise quiescent early type galaxies. And we say, what fraction of them have recent star formation? And as it turns out, that number is about 10%. And so what this is pointing to then is that galaxies, even the galaxies that everyone and their brother would agree are uninteresting and dead, when you look at them in the ultraviolet, 10% of them still have recent stars. So stars formed in the last billion years. The last billion years. Most of them have, the young stellar populations have ages on the order of a couple 100 million years, which is very young. You're still looking at sort of A star type populations. You're not looking at solar type stars at that point and at that age. And so the question is, well, where did it come from? Well, as we're finding out, I took the figure out just for time, but what we're finding is that galaxies which are more closely associated, or the more closely associated in a galaxy is with a companion, the more likely it is to show evidence of this recent star formation. So the conclusion that we're drawing in this paper that we're working on now is that galaxies continue to accrete material from their local environment, and that accreted material eventually goes into form new young stars. The second bit that I want to talk about is on cosmic reionization. So what does the ultraviolet tell us about the history of the universe? Well, here's the history of the universe in one slide. Pretty phenomenal that we can even make a slide like this in astrophysics. But we have the Big Bang on the left side. For a period of about 100,000 years, astrophysics was really dull. There weren't any stars to look at. It's all the realm of particle physics at that point. About 350,000 years ago, we had the CMB. So that's when astrophysics really kicks in. And then there was a period of time in which the first hydrogen atoms came into being. So naked little protons found naked little electrons zipping around in the universe. They combined. That formed the cosmic microwave background. And for a long time, those hydrogens just hung out. They didn't do anything. Eventually, though, the most overdense regions collapsed under gravity. They formed stars. And those stars presumably turned on. And those first stars to form would have been very massive. They would have emitted a tremendous amount of UV radiation. And that UV radiation would have leaked out of the galaxies, presumably, and ionized little bubbles of ionized hydrogen or neutral hydrogen around them. So in that, the dark ages, we say, when no stars were being formed, the dark ages eventually came to an end, maybe 10 million, 50 million years after the Big Bang. The first stars kicked in and they started to feed back in their local environment. The radiation started to destroy neutral hydrogen. And so if you wanted to, I'll skip that slide for now. You could simplify this entire picture down into one slide, an even simpler diagram, which is what is the history of hydrogen in the universe? And it would look something like this. So on the vertical axis, we have the fraction of ionized hydrogen as a function of time. On the left-hand side, we have the Big Bang. On the right-hand side, we have today. And what we have observed is that the neutral hydrogen in the early universe, when these protons first found electrons, was very, very rapidly, within a span of a few 100 million years, was very, very rapidly ionized. And now, no matter where we look in the space between galaxies, we always find hydrogen that is ionized, unbound electrons and unbound protons floating in free space. Periodically, these electrons and protons find each other, they recombine, but then the radiation field to which they're exposed is so strong that they're immediately ionized again. So the medium between galaxies is fully ionized in the present day. The question is, well, why? What happened? Well, as I said already, here's a simulation and I'll talk over it. This is a big box simulation. So we put all the physics that we have in astronomy, all the physics of that we have in physics, magnetohydrodynamics and radiative feedback and metal production. And we put all of this into a giant computational simulation. We run it on the most super of supercomputers, and we try to build a universe. And in these models of the universe, I'll let it get through the introduction, we can track what galaxies are doing over time and under the physics that we've put into the simulation. And what you'll notice here is you see this like tenuous sort of web of material. This is all the most overdense regions. So this is where high concentrations and high densities of gas are. And you'll notice along this web, there are these little nodules, and those nodules are places that are the formation sites for massive galaxies, groups of galaxies, and clusters. And over time, these clusters and these individual galaxies merge together. And what you hopefully see and hopefully it comes out in the big screen there, you'll see that when these galaxies do merge together, there are these massive bursts, and you see material being blown off away from these sites. And that's because of stellar feedback and feedback from AGN. When stars explode, they impart a tremendous amount of mechanical feedback into the local environment. They push out the gas, they destroy the gas, and presumably the theory goes that this feedback opens up channels through which the hot stars in the interior can emit their radiation, their Lyman continuum, their ionizing hydrogen radiation, can get out of these galaxies. And if they can get out of the galaxies, then they're going to find neutral hydrogen in the vicinity and they're going to ionize it all. And that's a wonderful theory. The problem is that we very rarely see this happening. And it should always make anyone uncomfortable that if you have a perfect theory, but your observations never back it up, then you have some work to do. Either you have to make better observations, or your theory of star formation and evolution is wrong. So we don't know which is which. Now, in the early universe, there's a lot of neutral hydrogen between us and those sources. So we can't ever do this observation directly in situ. We can't look at the first galaxies, even if we could find them. We can't look at the first galaxies and try to determine how much radiation is leaking out of them. And so we do this in the local and low redshift universe by looking directly in, of course, the ultraviolet for this ionizing radiation escaping from galaxies. And in my lifetime, we've gone from having about 2 to having about 100 of these galaxies. And much of my early career in astrophysics, or my postdoc, I was a postdoc at the U for a few years. Most of my time at the U was spent in trying to find this escaping radiation. And if you've ever wondered what astrophysical noise looks like, this is just like the noise you get on your TV screen. You shouldn't see any structure here. And that's because when we took all of these individual images of galaxies we expected to find this radiation escaping from, we found nothing. We stacked them all together in order to improve the signal to noise, and in none of the stacks did we ever find anything leaking out. And this is a real problem because these galaxies that we selected are supposed to be the analogs of the high redshift galaxies, the distant galaxies that are producing this sort of ionizing radiation that caused the ionization history or the profile that I showed you a few slides ago. Now, in the past 5 years, we've done a lot better. I've been involved with a couple of proposals, one on HST, or a couple on HST. Here's a plot of the vertical axis. Here is the observed Lyman continuum, or the ionizing radiation that escapes from observations of galaxies, some of which are shown on the right. And it's always good when you don't have upper limits, but you have open circles. Open circles here indicate detections. We now have lots of galaxies detected, not tremendously large numbers, not a diversity of galaxies, but we do have detections, period. So we can start to answer the question, what are the conditions necessary in order for this radiation to escape? 5 years ago, literally, we couldn't answer that question. We were totally flummoxed because wherever we looked, and there were lots of people who looked, wherever we looked, we never found this radiation escaping in the ultraviolet. I want to point out one particular one that I'm proud of. And I just pointed this out because I know some of you are probably wondering in the crowd, like, do people even go outside anymore? Do people even go to observatories anymore? Or do you just sit in your pajamas and download your data from HST while you're drinking coffee? And I want to show you that, yes, we stay up all night working on this data. Here's an email that I had with an individual at IUCA, which is the Indian Space Research Organization based just outside of it's in Pune. And here's an email. At the time, I was a postdoc at Stockholm University, and I sent this email to him. He had said, Michael, I have some new data with an Indian space observatory that had UV capability, UV imaging capability. And he said, I've got this data. Is there any place I should look to see if there's Lyman continuum escaping? And I emailed him back. And I very excited because UV data is very hard to come by. And I said, look at these two sources. And I think there's only one source you should really look at because this is the only one that our theory would predict is a strong leaker. So I just made a screenshot of this email. So he looked at it. Here's the source. The red arrow is pointing to the source in the field where we had the data. And here is the image. The top image is sort of optical, and the bottom image is that Lyman continuum. And sure enough, there's a booming Lyman continuum or ionizing radiation signature for this galaxy. So we wrote a Nature paper on it. I got very excited because finally, after years of searching for this, I finally had a galaxy where we could find this at a redshift regime, which no one had found one before. So it was really exciting times. And we've been doing this ever since in greater and greater numbers. Okay, now, I promised you JWST. It's 8:45. So we'll get through JWST now, a little bit of what I'm doing and a little bit of what the community in general is doing. So what would an astronomer do with a few $10 billion? Well, obviously, I would tell you, you build an ultraviolet telescope. So that's what we did. We built the James Webb Space Telescope, which is the most advanced infrared telescope ever developed. And you say, well, Michael, you just told me for 45 minutes that the UV is how you want to understand star formation. Why in the world did we spend $12 billion launching the James Webb Space Telescope? Well, as it turns out, we built the world's best UV telescope. We just don't bill it as that. So here's what JWST brings to the table. It's observing exclusively, nearly exclusively in the near infrared. It has 3 cameras that work up to about 5 microns, so about 50,000 angstroms. And then it's got 1 instrument that works beyond that out to about 40 or so microns, which is, bona fide mid-infrared. So you've got near spec, near is, near cam, and the MIRI. 2 of these, or 1 of these, near cam is obviously a camera. The other 2 in the near infrared are both spectrographs. And both of these, even the near cam has the ability to do spectroscopy as well. So this is a spectroscopy heavy instrument or spectroscopy heavy payload. And the reason is because we really want to nail down what star formation is like over cosmic time. So what's the benefit of JWST? Here's a to scale model. So JWST is 6.5 meters in the honeycomb structure from side to side. Hubble is 2.4 meters. So at the wavelength regime at which they overlap, that's 3 times better resolution. So Webb is Hubble at the same wavelength range. Webb is much better than Hubble at the wavelength regime in which Hubble has no infrared access. So it's not really Hubble, it's really its own beast. Here's that same galaxy or that same region in the LMC again, but this is what 3 times better resolution gives you. I can't show the images side to side here, but just look at the tremendous amount of structure, the diversity of star forming, the diversity within the star forming region compared to the optical is totally different. The reason is because you're seeing different wavelengths of light. You're seeing deeper into the cluster. You're peering deeper into the dust. You're getting a much different view of star formation in this region. Now, for ultraviolet, the last bit is here's James Webb images distant galaxies as well as Hubble does for local galaxies. So here's a relatively low redshift galaxy, the Hubble on the left, and here's what the same galaxy looks like or in a simulation, but we now can do this for real. I'll show you with JWST. And the left-hand side, there's a box on there, and it shows you, there's a few bright pixels in there that you might think are interesting, but you can't really tell where the light is coming from. It's sort of spread out over that broad region. But when you look into JWST, you notice that there's a bright source right in the center of that box, and then 3 or 4 little clumps spread out. So now you know that star formation isn't extended over, in this case, a couple kiloparsecs, but instead it's sequestered to these little maybe tens or hundreds of parsec regions, which is really important for understanding how star formation is going to proceed in these galaxies. The dirty secret, though everyone will tell you it's an infrared telescope, is that JWST is a UV telescope if the universe you're interested in is redshifted into the infrared. So as the universe expands under Hubble expansion or cosmological expansion, literally the length of the meter changes. Galaxy's light is redshifted from the optical where it might be emitted, or the ultraviolet where it's emitted, by a factor of 1 times the redshift, or 1 plus the redshift, into what the operating bandpass is for Hubble. So if you put all these pieces together, if you take the ultraviolet, the true ultraviolet, observed ultraviolet from, say, Hubble in the low redshift universe, and then you combine it with the observed infrared, but the rest frame optical or UV in JWST's view of the high redshift universe, you can make sort of a flip book, if you will, or a yearbook. You can look at the galaxies over cosmic time, and the galaxies in the distant universe have to end up looking like the galaxies that we see here, and you can try to put these pieces together. How do galaxies evolve? How do they grow? How do they change their sizes? Does star formation vary in the same way? Or is star formation carried out in the local universe the same way it evolves in the high redshift universe? All of these questions we're starting to answer now in a way we couldn't with HST. So I'll show you one image of this. So this is I'm being a little unfair. I just took one filter image of a region in the goods field. And what you see here is this beautiful bright spiral galaxy right in the center. I'll call your attention to sort of the inner arm regions. If you find the spiral arms in this galaxy, you'll notice that they're fairly empty. There's little clumps, a little string of pearls, if you will, that run along the spiral arms of that spiral galaxy. But there's not much else going on. And in the vicinity, you see there's lots of other galaxies in the background, but they're just, small blips. Now, if we look at the new James Webb data that came from the Sears team, This is that same field, but observed in the infrared. So the same galaxy, and immediately, now it's a color image, so things pop out a little bit more. But if you look at the near infrared image, even within that spiral galaxy, there's a tremendous number of structures that simply weren't observed with Hubble that are now visible in the infrared. So that's what JWST can give us in terms of resolution for understanding galaxy formation and evolution. So where's JWST right now? Just for reference, I always point this out because there's always someone who says, did we go to space because it puts us closer to that field we're interested in? Well, we did get a little bit closer, but only about 1 million miles closer. And these galaxies are billions of light years away. So 1 million miles versus 1 billion light years really, really doesn't help us out too much. JWST sits out at what's called L2. It sits in a halo orbit around L2. This is a place in which the gravitational force balances out with the centripetal force exerted on that spacecraft. So for very little energy, we can park it in that orbit and keep it there without it moving inward or outward. When we observe, we always have to keep that giant sun shield. So for scale, that giant sun shield on the bottom of JWST, that's about the size of a tennis court. And we keep that sun shield pointed sort of butt end towards the sun. We have a large viewing range that we can look at over the sky at any given time. And though not the whole sky is visible over the course of the year, it too will make an orbit around the sun. And so the whole sky can be made visible. It also has the capability of observing with multiple instruments at once. Here's sort of the right-hand figure is showing where those instruments lie on the field of view. So you could turn on near cam, you could take images with the near cam, but then you could also turn on near spec and get data for free, but separated by about 4 arc minutes. The JWST has the capability of running more than one of these instruments at a time. Hubble could do this too, of course, but this really makes it a much more efficient, or this can make it a much more efficient telescope than simply pointing at the one object that someone thinks is interesting and everybody else has to wait. You can kind of think of this as sort of like operating like a chameleon's eyeballs, for example. One eye can be looking somewhere and the other eye can be looking elsewhere, and 2 people can be satisfied at once looking at one field of view. So what are we doing with new science? Well, on my end, I'm involved with 2 large projects. The first of these is pearls. Here's a view. This is sort of hot off the presses. This is a mosaic of pointings with the near cam instrument. Here you're seeing sort of 1.1 to 1.8 micron data. This is a strip taken around, a field of view taken around the North Ecliptic Pole. If you go back here, I'll show you again. The North Ecliptic Pole is a very special place because it's always visible with HST. And that's really important because JWST doesn't have to move to find it. It doesn't have to do any extra additional rotation to put that field of view. It only has to rotate about 1 axis in order to find that point of view. So it's very easy to schedule. And the people at Space Telescope who are operating it, they love when you can say, well, you only have to spin up 1 gyroscope in order to rotate it into the field of view. You don't have to run 2 or 3 because everybody wants to use these as few times as possible in order to make it live as long as possible without breaking down. And breaking down is a big deal with JWST because there is no way to salvage it. With Hubble, if something broke, in principle, you could send up a space shuttle with astronauts to strip out the broken stuff and put in new material or new instruments. You can't do that with JWST. It may be possible in the future, but it's not clear. It's certainly not built to be repaired. So if it breaks, it's broken and you can't do anything about it. So let's not break it by doing lots of complicated maneuvering. So we're looking at the North Ecliptic Pole. This is a strip. I just point this out because it's beautiful. There is a tremendous amount of structure in the field. We also are looking at relatively local galaxies. Here's a overlapping pair of galaxies. It looks like these 2 are merging, but in this case, it's called VV191. These galaxies, one is just slightly ahead of the other. They're not actually interacting with each other. My interest in this was that if you notice on that elliptical galaxy, that early type galaxy, the left-hand side galaxy here, maybe you can see just off of the center, slightly at maybe 300 degrees from east, from straight up. If you go around clockwise, you'll see a little arc there, a little red arc. That's actually a cosmic lens. In Hubble, we didn't even see it. It was just barely there, but there wasn't enough data to really convince ourselves that there was a real feature there. But in JWST, it pops right out. This is a galaxy which is about 6 billion light years behind the galaxies that we're looking at. But because of the mass of the galaxy, it distorts the light from the distant galaxy, producing this cosmic lens. This is exactly as predicted by Einstein. We now observe this all the time. And in fact, we're able to do this sort of do science of resolved stellar populations. In fact, individual stars at 12 billion light years away by taking advantage of this cosmic lensing principle. Here's another program I'm involved with. This is a huge program, the largest program JWST will probably ever be engaged in. This is called Passages. Here's a field of view of Passages. You'll see all these points are individual galaxies with the exception of a handful of stars. But I told you that JWST has this spectroscopic mode. You can look at individual galaxies and get an individual spectrum, or you can put a prism basically in front of the field of view and you can get a grism image, a grating plus a prism. It's called a grism. And you can get every object in this field of view, you can get a spectrum for it. Now, it's a horrible field to look at because everything's overlapping and the spectra are, there's multiple orders on the same chip. But each of these little rainbows that you see here, each of these little streaks is an individual galaxy spectrum. And if you're interested in finding hydrogen alpha or oxygen 3 or silicon lines for metallicities, this is what you want. And you can do this now, not at redshift 0 or redshift 0.001, the local universe. You can now do it at redshift 3. So here's a galaxy at redshift 2.78. You're looking at a galaxy that was born a billion years after the Big Bang, a billion. So this was born when the universe was, 10% its current age. And you can clearly see in the spectrum, the middle, the second row from the top, that red bumpy curve, those lines, those emission lines that you see, those peaks, are associated with the hydrogen beta and the oxygen 3 lines in the optical for this galaxy. So you can use those to understand star formation and metallicities and the ionizing radiation field within this galaxy itself. So you can do tremendous science on these galaxies. Now, in the last 2 minutes, I'll talk about what everyone else is doing. So I'll start locally and move our way out. So first of all, JWST is not designed just to do star formation. It's designed to do, for example, planetary science in our own solar system, as well as detecting other planets around other stars. And locally, how will it do that? This is I guess about as hot off the press as you can. A couple of weeks ago, I was in Seattle for the AAS meeting, and I hope you can read it. But in the first cycle, JWST has observed 26 Earth-sized extrasolar planets, planets around other stars like the Earth, at least in terms of their mass, in order to determine whether they also have carbon dioxide and water and so on, 13 Neptune-sized planets, and 23 Jupiter-sized planets. So in the first year, we've observed 50 planets, and we were able to observe them looking for features like these: carbon dioxide, oxygen lines, methane, water. The reason we want to study these with JWST is because if we can find absorption by water in the atmosphere, that's the signpost. That's the bare minimum you need to support life. If you can find carbon dioxide or ozone, or you can't find ozone in the infrared, but if you can find oxygen lines, especially if the oxygen lines seem to vary between the day and night side of the planet, you may very well have a strong case for the presence of life affecting the carbon or the oxygen abundance in the atmosphere. You're never going to shake a hand with an alien. The first discovery is not going to be aliens landing on the White House lawn saying, "Take us to your leader." The first time we detect alien life is going to be through variations or the detections in the spectra of distant extrasolar planets where we see this variation occurring due to the presence of life on the surface or in the atmosphere. Here's everyone's favorite planet. This is Neptune. Here's Neptune imaged with JWST. It's always fun to put this one up because everyone thinks it's Saturn because it has this beautiful ring system. But no, this is Neptune. And what I'll call out is these bright spots, these hot spots on Neptune. We don't understand Neptune. We've never been there. We've only zipped by very quickly and took some pictures on our way out of the solar system. But we don't understand why Neptune is the way it is. In particular, Neptune's hotter than we would expect. And we don't know why it's hotter. What is happening in order to produce heat in the upper atmosphere that gives rise to storm structures or large scale climate variations in the system. The idea here is that there's some complex chemistry that, you know, it's hard to reproduce here on Earth-based laboratories, but we don't have any data to test those ideas yet. JWST is providing those data today. Here's a beautiful Wolf-Rayet star. You're seeing 100 years of dust being ejected off of this star in periodic pulsations. And as the light from the star is emitted, it reflects or bounces off of the dust grains that were emitted previously, and you get this shell of structures. You can think of this as bubbles of dust emitted from the surface of this star. Very beautiful, very important for understanding the late stage evolution and the deaths of these massive stars. As we move to even farther distances, here is a star that is 12.9 billion light years, billion with a B, light years from us. The star is not the thing that looks like a star there with the spikes, but it's actually that faint red streak that you see off to the right. And I wish I was there to be able to point it out to you, but there's a small pinprick of light. There's a red streak. This is a single star, a B star, about 50 times the mass of the sun, that is just so happens to sit right on the cusp of one of these cosmic lenses I referred to, that we're able to visually detect and resolve as an individual star. We are doing stellar astrophysics for stars that are 13 billion light years away. If that doesn't blow your mind, I don't know what will. Here is the current record holder for the most distant galaxy ever observed. This is JADE's GS-Z13-0. It's from the JADE survey. It's this little red blob on the far right. The former record holder was at redshift 11. Redshift 13 corresponds to an age in the universe of about 300 million years. This galaxy formed or is observed as it existed about 350 million years after the Big Bang. All of the stars that formed in this galaxy had to have formed very quickly in order to produce the signal that we observe. It's a very massive galaxy, or not very massive galaxy, but it's energetically forming stars, and there's a lot of mass to it. It's hard to nail down the mass, but it's not a Milky Way mass, but it's within 1/100th of the Milky Way. So it's not nothing. And how those galaxies came to be is a topic of very contentious debate right now in the community. Coming back to the more local universe, as we look at galaxies at redshift 3 and greater, so now we're looking at galaxies as they existed maybe 2 billion years or so after the Big Bang, or 10 billion years ago. What we're finding, in fact, is that there are a lot of galaxies that are much bigger, much more disk-like than we would expect, and this is becoming a big problem for simulations of galaxy evolution. There are lots of press releases that use the terms like too big or too mature, too hot, too young, too early. There are a lot of galaxies which seem to have disk features that formed within, say, the first billion years of the first billion years of the universe. And that's a big deal because it's really hard to get all that mass together to form the structure that is a disk-like rotation. So, you know, this is hot off the press. This was released in January 12th, January 11th. So we've only been looking at it for a month, and there are going to be lots of papers to come in the meantime or in the future to try to explain why this is the way it is. And I'll stop there. It's 9:05. Hopefully no one fell asleep, and I hope there's still people in the crowd. Not everyone left at 9. But if you have any questions, I haven't been checking the chat menu, but I would say come visit me in Mankato if you want. If you're ever down in this area, I live on campus, and I live in Mankato. But if you want to ask me a question here, I could try to address it as best I can in the short term, or you can just send me an email. I'm happy to chat more offline if there's something that particularly piques your curiosity. So
Yeah, if there's any questions, just unmute and ask if you would like to ask Michael some questions.
Rutkowski, question. One of my, shall we say, favorite little astronomical oddities are the what's called the Death Stars, black holes that do the gamma ray bursts and such. Do they cause a bit of havoc in that regards? I have a second question to ask after that, a little funny one.
They do. They cause a big problem, which is that we are finding the most massive black holes much earlier than we might have anticipated. And this goes back to the problem of, too big, too mature, too early. In order to, the current theory of how we form a black hole is you start off with stellar mass black holes, 50 solar mass star goes kaboom as a supernova. It collapses directly to form it collapses to form a black hole. And that black hole has a mass of, 35 solar masses, let's say. That 35 solar mass star forms in a cluster with lots of other 50 solar mass stars that also go kaboom. And those 35 solar mass black holes all merge together to form a few hundred and then a few thousand. And then hopefully they get drawn towards the centers of galaxies and you start to build up million and billion solar mass black holes. And then you turn on what the quasars turn on during that accretion process. And those quasars have masses of, 1 million to 1 billion solar masses. The problem is we're finding quasars at much higher redshifts than we would expect, with masses that are much higher than we would expect. And so the question is our theory for black hole formation correct, that they build it up from small ones, or do we need the more exotic solution is primordial black holes that formed with the Big Bang itself? Or do we have, say, the ability to take 1,000 solar mass cloud and directly collapse it to form a 500 solar mass black hole, so that we now are combining 500 and 500 instead of 35, because it takes 10 mergers of those in order to get up to 1,000 solar masses, where it only takes 2 mergers and much less time to get up to the same mass. So it's a great question. It is causing trouble. If you wanted to look into this further, look into I'll put it in the chat. Haojing Yan does a lot of work, and he had a press release at the AAS where he was looking at high redshift quasars that were a little bit bigger than we would have anticipated, and that's a problem because we don't know how to make them that quickly.
The second question I have, get a nice chuckle from you. Are you in competition with NOAA? NOAA in this case, the nominal description is no National Atmospheric and Ocean such. The other description is the National Organization for Advancement of Acronyms. I'm looking at some of the descriptions. You have so many acronyms. I'm wondering, how do you keep track of them?
Oh, yeah. We love acronyms. So we have passages, which was the I wrote a proposal which was census, the census 2175, the census of extragalactic galaxies in the near UV, search for ultraviolet spectroscopy at 2175 things. We love acronyms because we're lazy. We have it's an unwritten rule that if you don't have a good acronym, I think your chances of getting your proposal accepted, you might lose points. I've tried to come up with, I've gotten to A through J. I once came up with a survey which was the ABCDEFGHIJ survey, just to see how ridiculous we could get. And I mentioned we're all adults here, but my favorite acronym of all time was the Super Huge Interferometric Telescope, which was proposed by students at the University of Arizona as an April Fool's joke, to combine thousands of individual Dobsonian, SkyQuest type Dobsonians together to form a giant interferometer. The acronym for that takes the cake. But yeah, acronyms are everywhere. We can't get away from it.
Are there any questions on the in-house?
I see Ron Schmidt has a question raised, a hand raised.
I do. I have my hand quietly raised here in cyberspace. Hey, I was wondering, I never saw very many results from the Hopkins ultraviolet scope that flew on STS-35 and STS-67 back in 90 and 95 on the back of the space shuttle. Did you get to see any data from that instrument? And was that a successful distribution of a telescope sitting on the back in the payload bay of the shuttle?
Yeah, it was a fantastic telescope. It was, so I think it was launched from Johns Hopkins. It didn't, I think part of it was that it wasn't, it was on a space shuttle, and space shuttles don't stay up very long.
Right.
So it didn't, I think it got like 100 objects. And a lot of the people who were involved with the development of that telescope were very much focused on, it made tremendous, or first attempts at finding, at observing the metals in the line of sight towards distant stars. And I think for that reason, because it observed a lot of stars and not so many galaxies, the stellar astronomy field, the people who are obsessed with looking for, metal absorption lines along the line of sight and sort of trying to understand the interstellar medium, that's a very relatively niche community within astrophysics. It was a tremendously successful program. I mean, there was weren't there 2 of them even? So I think there were
2 telescopes?
was there a Hut 1 and a Hut 2, or was it 2 different missions?
I just remember the one scope on 2 different missions.
Oh, okay. So
90 on STS-35 and 95 on STS-67.
Yeah, it was. I mean, I don't want to date myself here, but it launched, I believe, when I was in, I want to say elementary school.
Oh wow, look at the time. Okay.
Yeah, and but in looking back, so I can tell you, one, I have a book on my desk in which there are the spectra from this telescope for individual stars. So O-type stars and B-type stars, some of the calibrated spectra came from Hut. And then there was also, at the time when like high redshift was like redshift 2 or 1, there was I know Hut had observations of quasars, so they were able to detect the intergalactic medium, and look for metals and the state of metals in the space between galaxies, not just within the galaxies itself. And that was, in the 1990s, there was no one else in that game doing high redshift quasars. It really wasn't until, to be honest, I don't think it was until the Sloan Digital Sky Survey came around that people started to collect huge samples of quasars and look for the absorption of neutral hydrogen in the spectra, and try to determine from that direction how the universe had been ionized to that since the time of the quasar emission. But Hut, I guess if you were to plot the number of quasars observed at high redshift, you would have the radio community was doing a lot of them. And then Hut was, and I guess OAO and IUE. IUE is the granddaddy of them all. IUE was the king of these UV telescopes, so to speak, in terms of the science results. But these would always target these bright stars. They go after Vega and they go after a quasar.
Sure.
And that might be the only targets they get that day or something. And those data were, they were the only data available. So it certainly made an impact. Probably, it also happened around the time of Hubble. And, it's also the downside, to a lot of the UV, and especially the NASA, the JWST science, is that a lot of it is spectroscopy. And spectroscopy doesn't look as pretty as an image. And when Hubble started making, when Hubble's was, the corrective lens was applied, when the correction was made and it came into view, there were lots of pretty galaxies, and not too many people were concerned about what oxygen 6 looks like, 5 times ionized oxygen looks like along the line of sight to some bright star at 10 parsecs away.
Sure.
And so I think, maybe if they had Twitter, they could have been more popular. But I think it was just there's only so much bandwidth for the public. I mean, it did great science. It just maybe didn't make as big a splash as some of the other.
Well, and quick question, follow more recently we had the Galix decommissioned in 2013. Is there a plan to put up a UV dedicated satellite again, or are we just gonna, get what we can out of JWST?
There are two. There are more than, there's more than one. There is a proposal. I couldn't make the meeting, but there was a plenary session at the AAS this year to do a follow-up to larger than Galax, but Galax style instrument to fill that hole, because eventually Hubble will die, and Hubble is really our only access right now in many ways to that sort of imaging. So those are always contentious, but there's going to be I think it's a mid-X mission. The mid-X mission after Galax became a little controversial because mid-X was supposed to be capped, I think, at 100 million, and then Galax was renewed, and it ended up costing a few $100 million, and a lot of other people got angry because, are eating into their pies, so to speak. But this is supposed to be, a couple $100 million mission. I will mention that at Mankato via UC Boulder, we are launching a CubeSat, which is going to actually be sort of a Galax-like in terms of spectroscopy to look for Lyman continuum and supernovae. That'll launch in 2024. So we will have some new UV data coming from that for 6 months or so until it burns up in the atmosphere. And then finally, on longer timescales, like when I'm retiring potentially, if you can imagine such a timescale, there is a competition in the 2020 Astro Decadal Review. The programs that were advanced as potential new great observatories, there was an X-ray mission, LINX, and there were 2 UV optical capable telescopes that would operate, and these would be telescopes. The bigger one is called LUVOIR. It doesn't have a real name yet. The large UV optical infrared telescope, and this would be JWST times 6. It would be a 10-meter UV capable telescope built in the same style as JWST. It sort of folds up in a cocoon at the top of the nose cone of I don't even know if they have a rocket big enough to launch this yet, but some Ariane 5 rocket or something, and then it would unfold in space, and you would be able to fit, I think, 4 JWSTs within this telescope. The problem with this is if JWST costs $12 billion, this telescope is going to cost something like $40 billion. And we're coming to a point at which, if you try to satisfy everyone that wants UV data, you end up satisfying no one, because in order to get the spectroscopy you need of extrasolar planets and to look for high redshift galaxies, you don't have enough time, period, to do all these things. And so there's a real tension in the community about whether we will build another giant telescope like James Webb that would be able to do the UV or the optical, primarily for planetary science, but for stellar physics and stellar astrophysics in the local universe as well as all of this Lyman continuum science and stellar evolution and galaxy evolution in the local universe. But will that fly? One will fly, but I can't imagine Congress ever approving, $40+ billion for one telescope after what happened with James Webb, where we had to fight for James Webb because, it was on the chopping block every other year because it was so difficult to make.
Hey, Michael, I'm
Yeah.
sorry to interrupt, but I'm sorry. We
You lose
love
the
your
room.
presentations. This is the president, sorry.
Yep.
I'm sorry, we have to wrap it up because we got to go.
Sure.
So, but thank you very much, everybody.
course.
We appreciate that. We'll give it a little clap in the room here so you can hear. Thank you, and everyone have a great night, and we will all see you next month. Take care.
All right.